you hear now?
Yes, I can hear you.
Perfect. Thank you.
Mhm.
All right. So hopefully you get more information from the Excel sheet about how we design these devices, what are the design choices, and how manufacturer look into the device and make the choices between trade-off between the price, capacity, and the power consumptions. So today we'll be talking about different flavor, which is processing in memory. That is still related to everything we've been seeing until today, including the caches, the main memory device. So this is lecture 8. So again, back to our story. Whenever we want to fetch any data from the storage, we have to move it to the memory caches all the way to the CPU. And every time we make that move, it's a really expensive move because all that cost need to be added up. So you move a data from here to there, you have to pay that penalty. You move the data from there to here, you have to pay that penalty X in addition to whatever we paid over there. And you keep adding the cost until your data reaching the CPU. So it's really very expensive to move those data. And this is what we call as data movement. So data movement is every time we move the data in order to do some processing at the CPU side. The data movement could also happen inside the CPU because inside the CPU might be more than one processing core. The processing core not necessarily to be ALU or arithmetic logical unit, but might be the GPU itself. It might be the encoder for the voice, for the camera. There are a lot of decoding, encoding stuff to process the images and the video that we have. Data movement in today's computer system really dominates the performance and is a major system energy bottleneck. What does it mean? It means the main goal of those computing system is to compute, right? However, when we look at the total energy spectrum, we see that moving the data is consuming most of the energy spent in those systems. Although the main purpose is to do the computation, but data movement is dominating the entire system. If we look at some of the analysis, there are a lot of papers, so you'll see a lot of those numbers, different numbers, depending on the application. But one of them, which is very important one, try to analyze the workload in Google workload, Google data center. That's including Chrome browsing, the YouTube, advertisement, Gmail, and so on. So they claim that about 62% of the total energy spent in today's computers is just about data movement. Those numbers, as I said, you can see them really in different, somewhere between 35 to 62, but can be more depending on the pattern of the application. If the application really visiting the memory very often, then that number really increasing. There is other studies showing that moving the data from the DRAM to the caches, L2 cache, L1 cache, all the way to do the computation over there, it's about 138x much more energy than the computation itself done at the CPU. So this is for 8-bit multiplication. And you can do the math, but you need to add all those energy up, the numbers, until you can compare it with the multiplication. There is more studies about that. 62.7% of the total energy spent on data movement. However, when we compare the energy spent for those data movement, we will see that it's about 160x to 800 more energy than the addition or add operation done at the CPU. So we pay a lot of cost just to move the operand from the data or the memory all the way to the CPU to do just little operation on that. And that is really a big problem for us. Now, what is the reason for data movement bottleneck? Why it's a problem? We actually, in fact, did that in purpose. In the first 3 lectures, we saw together how by not doing memory hierarchy, we are going to pay a lot of cost, a lot of storage penalty, because the SRAM, which is the fastest memory that can understand or cope with the CPU bandwidth or computation processing power, it's very expensive to do. So we cannot have the SRAM only connected to the CPU. So we try to use a minimal amount of the SRAM since it's very expensive and try to substitute the difference in terms of speed and cost by having a cheap DRAM. Now the DRAM, the capacity is really large and very cheap to use, right? But it's very slow. Why it was slow? Capacitors, that's one. What's wrong with the capacitor? You cannot hold charge. Yeah, they leaks over time. What else? We need to recharge or pre-charge every time we read it. What else? That's a big win in the first 5 minutes. She presented, right? She deserved one. So we have to refresh it because it's leaking over time, right? So we have to refresh the entire device. It's not single row. But every time we read a row, we need to refresh that in particular also. And that makes the process really slow. But also, we have a problem with data locality. We designed those caches to solve two problems, temporal locality and spatial locality, right? However, even if we do that in purpose, we are moving data that might not be used in the near future. So we move a lot of blocks of data, but at the end of the day, we may trash them. But also in the same thing, we might move a data that is very useful, and we are going to use it, but due to the replacement policy, we are going to evact it, remove it from the cache, and every time we want to reuse it again, we go back to the DRAM, bring it again, right? So there is always a problem with the data locality, either as useful or as a thing that we bring and we will not going to use it. So something not useful. There is also a problem with the memory bandwidth. We know that the interface restricts us from not transferring more data. So we are always allowed to transfer only 64 bits, which is something very small. And that is creating a lot of complexity with the architecture if we want to increase the interface width. The average memory access time is really high for several reasons. And there are a lot of problems about the access time. And we define the latency last time as, what is the latency of DRAM device? Whenever a memory controller sends a request to the DRAM device and the DRAM device responded back, then that is the total latency for a DRAM device. Okay, so we include the round trip of the whole thing, right? So it's not only that. We know that the memory device is not scaling well. We increase the bandwidth. The applications are becoming really hungry for more data. The CPU becoming much faster because this transistor getting smaller in size, so we can fit more transistor in very small area of silicon. But the memory device is not scaling, and that's what we call memory wall. And we saw that problem also happening with the AI application. There's the transformer size really growing much faster than what we have in the memory devices. So what is the solution to all of this? If you think about it, we see the problem that we have one place for computation, we have many other places for memory or storage. Then one idea is to bring the processing elements next to where we're storing the data itself, right? Because if we keep bringing the data and go back and forth, just to do a little computation, that is a waste of a lot of cycles. But if we know that we are going to use often a single computation, which could be anything, any bitwise operation, and or XOR, for example, then we could enable this kind of processing where we are storing the data, and no need really to pass it through the entire hierarchy of the memory. So data analysis is performed far away from the data. Hopefully this is clear, and we emphasize it a lot. And that all going back to the Neumann model that was proposed in 1945. So all today computer are still following that von Neumann model, which is, okay, yeah, it's good doing the general purpose computing, but as we move to more sophisticated application, more data hungry, more memory intensive application, this paradigm becoming really outdated. So we need really to do a paradigm shift, making the computing architecture more data-centric, meaning that rather than being compute-centric, so everyone trying to obey the order of the processor, now the memory is dictating the system. So everyone should obeying the order of the memory itself. So the CPU sending whatever processing power to the memory itself to enable that. And that's what we call as a data-centric. Enabling computation with minimal data movement, because data movement, again, it's a problem. Every time we deal with interconnect between several components, we are going to pay a lot of energy for that. Compute where it makes sense or where data resides, basically. This slide's more about futuristic designs, futuristic architectures. So you're going to hear maybe terms for the first time, you maybe hear it. Something like intelligent hardware aware optimizations and algorithms. We already study a few examples of this. For example, loop interchange, blocking, those kind of optimization that we can do. And they are still aware about what's happening in the hardware. We know that the hardware will benefit from certain way of programming the code. Then we design our code to follow this procedure. So most of you are probably aware about what's happening over here, which is specialized code. For example, I'm suffering from slow computation in the CPU, then I go and accelerate all these processing in FPGA, in GPU, in AI engine, right? That's what mostly we are doing. However, recently we start hearing something about intelligent cache, intelligent memory, intelligent storage, intelligent data generator. So data generator could be a camera. So rather than I connect the camera to a laptop, I could do the processing inside the camera itself by enabling the computation where I generate the data itself. Anytime I mention intelligent, it means there is a computation happening over there. But also we start seeing something fundamentally new computing or fundamentally different storage architecture, something never we've seen before. So we all know about the SSD, the DRAM, the SRAM, right? The caches, the DRAM, and all those memory devices. But recently we start hearing about totally different memory architecture. Let's see a few examples of that. How many of you are aware about Microsoft Analog computers? This is just announced this month. This is very recent. How many of you are aware about that? None? Okay. Then this is a good opportunity for you to learn about it. There's a link over there. You can visit it. So this is how it looks like. Nothing similar to today computers. What it does, it solves problem 100x faster or more energy efficiently than digital systems, which is today computer. We are dealing with binary data, 1 and 0. But over here, it's just optical device. It's just dealing with light and physics. That's it. You impose a certain light, and that will encourage or motivate the computer to do certain computation. Leverages the parallelism of light and physical process to perform computation and avoiding the separation of compute from memory. And this is what we've been talking about. How it works? So they have two concepts. They consider whenever you transmit a light and you have it passing through a modulator, then that is performing a kind of multiplication operation, okay? Now how it works, why it's multiplication, not other operation, I have no idea. So this is all related to physics. But you can consider it like that. Whenever you have a light transmitted from one point to another, and you have a modulator which is spreading the light wave, then that is multiplication, because probably it's tried to multiply the waves by a number. So it's expanding the wavelength of each of those lights. But also they have a camera or receiver, and that receiver is considered as addition operation. So by having this architecture where you generate a light, you pass it through modulator, and then you have camera array to reflect those waves back to the modulator, you are doing multiplication and addition in the same time. By repeatedly doing that, that is a machine learning model. Because what is the main operation in any of those machine learning models or transformers? This operation, which is mul-add. Mul-add means multiplication and addition. So whenever you enable that process, that is the computation happening with the weights in the model. And by doing so many times, repeatedly, you are performing all those computation at the speed of light, which is much faster than doing that process in the transistor. Now, of course, someone could ask, this is really specialized computation, like can do only that operation, right? So what is the benefit of that? Now, it's okay to do something specialized rather than being general purpose, assuming that this architecture serves the most memory intensive application, which is AI. Until today, we are suffering a lot from processing AI application, and we need a lot of GPUs to do this operation. Here is another processor. This is a bit recent. Here's the paper I published in Nature Communication and 5 years ago. It simply works as following. You have two molecules, one of them red, one of them blue. You have a lot of or large number of motors. So this is small motors, and this is the fan of the motors. So whenever you rotate the motor, then you are going to do some chemical reaction between the blue molecule and the red molecule. Now, the rotation happening in those motors depends on the input. So wherever you program your input, that's going to be translated into certain speed of the motor and how many of them should operate. And based on all of those motion among the motors and their speed, the interaction between the two molecules is going to be different. And that's what's considered as computation. Then you are going, by the end, observe what's happening in the final picture. And if you can analyze it, convert it to something else, then you could infer the result, the final result. Now, how you program, how you correlate the input to the speed, how many of those motors should be connected, and all those questions, that's based on the application. So it's need a lot of experiment to correlate those information. But this is hopefully trying to give you some idea, and hence the need for redesigning or fundamentally having something in you. This is another thing. This is coming from ETH Zurich, my university in Switzerland. So what they try to have here, something called synthetic DNA. Synthetic DNA. You can think about it as 3D printers, but instead of having plastic, you have special material that recognize the DNA molecule. How many DNA molecules do we have in our bodies? We have 4. Okay. Adenine, guanine, cytosine, thymine. So you can call them A, C, G, and T. Adenine, cytosine, guanine, thymine. Okay. Those are the main components of your entire DNA. Your DNA is about 3.2 billion characters. 3.2 billion of those arrangements. Those are permutation made up your DNA sequence, right? So if you try to convert this molecule, which is originally found in our body, in plants, animal, and so on, if you could have a synthetic molecule that's manufactured in the lab, and then you could have special properties in that molecule to be frozen after some time, meaning becoming an object. Okay? So how you can infer or exploit such synthetic material? So you can encode data. For example, you can convert 0, 0 into A, 0, 1, 1, 0, and 1, 1 into T. So every time you have a message, for example, entire book, you want to store it in this kind of storage device, what you will do? First, you will bring the entire text, you convert it into equivalent binary code. For example, each character can be 1 byte, okay, or 2 bytes, 3 bytes, it's up to you. And you convert the entire sentence into those bytes, and then each byte convert into the binary equivalent, right? And now split the binaries into 2 bits. Now, based on every 2 bits, you can decide what is the right molecule I should use, okay? Whether it's A, C, G, T. So now I'm converting entire text, whole book, into a sequence of A, C, G, Ts. And remember, those are synthetic, okay? So it's easy to bind them, to make a sequence out of them, and then 3D print them. And this is what really they did. So they print that bunny, okay? That's the entire object. Try to store a whole YouTube video based on the same idea. Not only that, but they could also manufacture a glasses that is made out of the same material. So this object, as long as you keep it in room temperature, it's not going to isolate, it's not going to dissolve, it's not going to be affected at all. Okay, so something like it lasts forever and doesn't need power. It doesn't need any kind of energy to store the information. Anytime you want to retrieve back your data, you just need to do some kind of processing to the material and then feed it in a machine that we call sequencing machine, which is reading our actual DNA. The exact same machine, you could use it over here. You just take randomly, chop the sequences, feed it into sequencing machine, and then get back your DNA sequences, which you can convert to a book and so on. Now, of course, if you are working, I know 4 of you, 4 or 5 maybe, working on genomics, right? So there are a lot of problems with that. For example, when you do sequencing, you randomly read the object. You cannot know which sentence coming before which. So when you retrieve back the data from those 3D printed objects, you might not have the exact same book at the end, because some of the sentences, you need to align them, do assembly, compare them to a reference, which we don't have, and so on. All of those questions, same thing. So this is a real paper. You can look into it if you're interested in this kind of architecture. All right, so that just to give you a quick overview on different architecture, different storage platform. Now let's jump into processing in memory. So processing in memory is something that you can imagine. Until some point, maybe 8 years back, we don't have real devices that perform processing in memory. There were a lot of research papers trying to suggest architecture, how we can do processing inside DRAM, for example. Okay, but we never had real devices. Only until recently, we start seeing the companies producing a DRAM, a DIMM, write them, which whatever you can buy and purchase at your motherboard, and has computation power inside it. So you can program it, do some add operation, multiplication inside the DIMM itself. For that, it's really taking different forms. So where to enable the computation really? So one of the forms is basically this. You know, the memory controller is something that you can program where you send command to the memory. So you can enable computation inside the memory controller, okay? So you don't touch with the DIMM itself. In this way, you can stay aside from manufacturing problem, but you can reprogram the memory controller inside the CPU and try to avoid the caches. So you try to solve the problem with moving the data through 3 levels of caches, for example, and do something simple over there to move the data, process it over here, and move back the results. You could do, this is the most common currently in the manufactured DIMM, the actual DIMM that you have, is to have a specialized core inside the DIMM itself, okay? And one of the famous companies that's doing that called UpMem. This is a real company. It was a startup in France, now becoming a huge company, manufacturing those DIMM, where you have computational engines inside the DIMM. It's separated from the memory storage from the banks, so you still have the actual banks, but you do have additional computational engines or cores. The next form, which is something that you need to modify the DRAM itself. You need to modify the DRAM itself. So you need to play with the banks. You need to play with the DRAM chip, okay? Another form of doing computation inside the memory is something called 3D stacked memory. And it's really a 3D stack, as it says. Why? You see those green pieces? Those DRAM chip, the whole DRAM chip. So in every layer, there's a complete DRAM chip over there, okay? You stack them on top of each other, but not as separate chips, okay? Still, all of them are within the same package, meaning that there is no off-chip communication. Everything happening inside the package itself. That means we have very high-speed communication between them. So you can transfer the data much faster than having single data bus connecting all of them. And you have too many of them, which we call TSV or vias. Those vias, really many of them between every 2 layers of DRAM chip. Not only that, because, okay, yeah, we have a lot of DRAM chip, where is the computation? We usually have a single layer of logic computation. And this logic computation normally reconfigurable. So you can think about it as FPGA fabric, which is an entire layer over there. And every time you want to do computation, you move the data from those layers of memory all the way to the PIM, do the processing, send back the result, and that's it. This device is a real device, and you can have it. You know the name of it? You see it in very expensive FPGAs, for example, or very expensive GPUs. What type of memory do we have in recent GPUs? The most expensive ones. For example, A100, H100. What do we have as memory over there? HBM. Excellent. What does it stand for? High bandwidth memory. So HBM. Normally, when you check most expensive GPUs, you don't see, sometimes you see DDR5, G, basically graphics DD something, but most of the memories in expensive GPUs, it's at HBM, high bandwidth memory. Why is that? For the same issues we discussed in the previous slides. So we really need to move the data in a high bandwidth. So you need a huge amount of data, which is the 3D stacked memory. But not only that, you need to bring the computation next to the where you store the data. So you can transfer a high amount of data to those logic layer, which can be anything. It could be FPGA, it could be GPU, it could be your own logic. You design it in CMOS and have your own transistor in that logic layer and fabricate. The last form of these is where you enable computation in the last piece of the architecture, which is the storage. You have SSD device, right? The hard drive, and you enable the computation over there. This is a simplified overview of the storage itself. This is SSD system. And amazingly, there is something weird in SSD device that they have their own DRAM. And inside the SSD device, the hard drive, they have their own DRAM. This DRAM is not used for your own data to be stored, but it's used to build pages out of the data stored. So you can consider it as a buffer or a cache for internal operation of the SSD. Now, whenever we talk about DRAM, there is always a need for a controller to control this operation. Because again, all the problem we discuss about DRAM exists here, which is refreshing, pre-charge, and fetching the data over banks, how you orchestrate the commands between multiple chips and so on, right? So since we have a controller, then directly we could do the exact same thing as in the first form and play with the controller command to do certain operation, okay? This normally the general overview of processing in memory. And if you see a lot of papers around the topic, it's really hard to be outside this group. There might be something different, but I'm not aware of. So most of the work that we deal with is either inside the storage, inside the DRAM, or inside the CPU itself. All right. So we talk about energy consumptions in today computers before doing processing in memory. And we talk about execution time. So the time to move the data is really huge. So whenever we deal with processing in memory, we assume two benefits. Improved performance, because we reduce the execution time, no need to pay all those penalties to move the data, but also to save energy. But now, since we already see different forms of memory, which one is the best? I have certain application. Where to run it? Should I purchase this architecture or this or that? here. So how we can decide on those? So the valid question is, what characteristics make an application a good fit for processing in memory? What is your guess? So we talk about several examples of application, for example, video gaming, AI applications, video, whatever of those applications, right? There is something so special in those applications that they have large requests to the memory. They might do computation, they might do little of those computation, but most of the time they request data to be brought to the CPU, to be processed, and then send it back to the storage. So how we could decide? Excellent. How we could know that? How we could know if an application is really requesting memory more than compute or compute more than memory? That's excellent if we are dealing with very old architecture, like single core CPU. But in today's machines, the CPU is busy with doing a lot of application, a lot of CPUs, a lot of cores, a lot of threads. How we can isolate to know exactly that those threads were dedicated to only my application. So if we only measure the bandwidth is really shared among all those applications. And the controllers try to be fair with all running applications. So your application is consuming this much of data, but I'm not going to satisfy all requests only to your application. I'm going to give a little bit to the operating system, to the video, to YouTube, to Gmail, to a bunch of applications running at the same time. Any guess? All right. So normally to understand that, we need something called vTune. vTune. So vTune is software you can run, you can download for free. It's provided by Intel. So we assume that you should have Intel CPU to run this application, right? What it does. So underneath it looks something like that. You have the application or the function call. So you know when you program something in C or in Java, you have a list of functions, okay? And each function is doing some computation inside it. So that name in the function call is exactly over here, okay? But also you can see some other columns which are very important. Each of them has really special meaning. I think Naeem is going to prepare a tutorial on this, right? So he will give you a lot of insights about it. But briefly, I'm going to explain these columns so you understand them if you even want to run it on your own by now. So there are two approaches in the vTune. One of them called top-down, and the other one called bottom-up. Okay. What we use for processing in memory is top-down approach. From top-down approach, meaning that you are located at the CPU itself, not at the memory. So these terms really will be coined based on where you are placed. If you are placed in the CPU, then your front end is anything happening at the CPU, and the back end, anything happening at the memory side. Is this clear? Okay. So let's start from front end. What's happening at the CPU side? If you understand these terms, you directly can remember everything happening in vTune. The front end basically is responsible for fetching and decoding the program. Okay, so we fetch and decode the instructions of your code. Now, what next? Right after I fetch and decode the instructions. So decoding means I understand the design or the architecture of each instruction. So I know now those 5 bits or 6 bits are responsible for operand 1, the next 6 bits about operand 2, and so on. Okay. So now if I understand that I need 3 operands, 2 of them for input and 1 of them for output, then what I can do is to go back to the memory and start requesting those operands in order to execute this instruction. And that's what we call a backend. Now, in the backend, we try to fetch the data operands, but also once we finish those data operands to be brought to the CPU, we continue executing the instructions. Okay? So we have front end, back end, and now the instruction being executed. What else? So there are two cases after executing the instruction. Either it's being completely executed, meaning that I'm done with it. So we just flush it from the buffer or from the queue. And that's what we call retiring, the instruction being retired. Retired means completely done, already executed, the output already stored, and so on. Now, if something happened in the middle of the way, I already got the operand, I already got everything, and now I'm executing it, but it's not completed for whatever reason. What we call it? Bad speculation. What does it mean? We already discussed it several times. What does bad speculation mean? Bad speculation. We discuss it as a way of improving your code. Yes, please. Don't be shy. Any guess? Branch prediction. Excellent. You got one today? No? So branch prediction, what does it mean? What does it mean? Branch prediction. So we said whenever the CPU is stalled for whatever reason, meaning that I'm not processing anything, I already fetch an instruction, I decode it, I know that I need two operands, but now the memory is busy. So I cannot continue executing it because I cannot get those two operands. So if I'm doing, for example, this operation, so I need these two operands, right, in order to execute the addition. Okay? So if the memory is busy and is not feeding me with those operands, then I cannot continue executing. So, but the CPU is smart, is able to process a lot of instructions. While waiting for this, they jump, they skip the instruction, and they move somewhere else. They start fetching the next instructions and try to execute it. And that's what we call as a branch prediction. Assuming there is if statement somewhere, if this is true, do this, if not, do that. So this is where we call it branch. Branch because you could either branch to this or branch somewhere else depending on the condition over there. The CPU make like speculation, prediction, right? And try to predict. I think the program will go more toward that branch over that branch. So I'm going to execute this, assuming that after the memory giving me X and Y and I execute this instruction, I will continue with that branch, not the other branch. And of course, whenever we talk about prediction, there is always some wrong guesses, some correct guesses. And that's what we call a bad speculation. So if the instruction was not fully completed, meaning that it was executing, but I realized late that this instruction that I'm executing is bad prediction. Let's cancel the entire branch and move to the next branch because this is the correct one. Okay? So hopefully by covering those four directions, now you know most of the application either will be in this, busy in that, busy in here, busy in there, or busy in there. And this is exactly what you see in the previous picture. So this is where the classification happening from vTune. So it's going to tell you how many of the execution time or what percentage of the execution time your program was busy in any of the four clusters. Now, to give you more idea, so this is what's considered as pipeline slot, meaning that this is what you can consider as ALU or CPU. Okay, this is the processing unit itself. Now, in Intel microarchitecture, they consider the instruction going through the pipeline slot as micro operations. This is what they call them, which is the lowest level related to the actual hardware. You can consider it as machine code or assembly language and so on. Most of the Intel microarchitecture are able to handle 4 micro operations per cycle before the pipeline slot. And at the back end, they can also retire 4 micro operations per cycle, meaning that 4 instructions can enter the pipeline slot, and 4 of them can exit the pipeline slot per cycle, meaning that 4 of them only can retire, okay? And the rest can still be processed or being delayed in the pipeline slot because they cannot retire now. They have to wait for the next cycle. Now, if the micro operation, or basically the instruction, the assembly code, is waiting outside the pipeline slot, meaning that it's a front-end problem, so the fetch and decoding the instruction cannot happen now for some reason. Why? Because the Intel is limited to process only 4 per clock cycle. Only 4 can enter the pipeline slot. If I got 5 of this instruction, 4 of them can enter, 1 of them has to wait. And that is a front-end problem. Only at the fetch and decode level, okay? If it is a data operand obtaining or executing, that is a backend. So it could also be a backend problem if I have resource limitation, meaning that memory is busy or the core itself is busy. I cannot execute the instruction. All of those reasons can make the operation outside the pipeline slot. Now, once the operation entering the pipeline slot, there is only one case where the instruction cannot exit the pipeline slot, which is the bad speculation. So bad speculation will keep the operation inside the pipeline slot waiting or being terminated, just cancel and evicted. If it exits, it's mean retiring. Based on all those classification, you can understand further if you go in fine-grained detail. These are the 4 classes that we just discussed. Underneath each of them, you can see more details. For example, that the front end, which is fetching and decode, you'll see problem related to caches. Why caches is here? We said this is only fetch and decode. What caches has to do here? This is what we call I-cache. I-cache meaning instruction cache. Instruction cache. It's not related to data. This is where your program is buffered in a temporary memory as instruction cache, and every time I go to the cache, give me more instruction, give me more instructions. Okay, so don't get confused between the caches in here and the backend, because backend is responsible to bring data from memory, right? You can read this in your own, so you can see there's core problem in backend, memory problem, because we said execution happening in the core, but still we call it as a backend. All right, that was just to introduce you to a problem happening at Google data center. So this is the analysis happening at one of the data center in Google in 2015. And you can see their workload that is usually running in their data center. That includes YouTube, advertisement, Chrome, and all these applications that you are aware of. What you can see here is the analysis happening in vTune. So what percentage of time most of the instructions spent in Gmail being bad speculation, for example, or being retired, or being waiting at the front end or at the back end. So the green thing mean good, which is something retiring. So most of those instructions being executed in the good time, which is being serviced in 1 clock cycle. If we look at the pink, it means front end bound. And we said front end means instruction either being fetched or decoded. Okay, but if the having a problem like bounded by front end, meaning I cannot fetch them or I cannot decode them. Okay. Now the little red over there, which is something bad, that's why we call it bad speculation, because I did a prediction that's not related to the run. So it's, I predict myself that if or else. So I choose, for example, randomly if, or I choose randomly else. Why randomly I choose? Because one of the earlier instructions is still frozen. That's why I cannot usually execute the next instruction. I have to wait until this instruction being executed. And instead of waiting, I can just do that prediction and move on. But something weird that most of the application suffering from this large gap, almost like could be 70% over here, it could be maybe 40% over there, of the time just being back-end bounded. What does it mean? It means the instruction cannot be executed because a back-end problem, which is either the core is busy executing other instructions, so I cannot execute anymore, or the memory is busy. So do you remember last time when I told you, whenever you want to deal with your application and make it better, what is the first step that you have to do? All of you are doing PhD or masters, and at some point, you are interested in making your program much better. So what you would do? Vtune. The first step, vtune, right away. Run it, but there are some restrictions. So of course you need to have Intel processor. That's one. Second thing, you could use it as command line or interface, GUI. GUI, you have to go with Windows operating system, but you can run it on totally different machine than the one you are developing your code with, okay? And getting more insights about what's happening, and then you could get more into the problem. Either is it the cache, so I cannot do anything about it, or maybe I can use the optimization from compiler. So we discussed last time, when you use GCC to build your code, right? There are 3 levels of optimization. You could do -01, 02, or 03. Each of those doing different optimization to your code. One of them is loop interchange. Okay, so try itself, the compiler tries to understand your loops and try to replace if you have nested for loops, or sometimes try to unroll the for loop itself. What does it mean? Unrolling a loop. Unrolling a loop. What does it mean? Instead, if you have like very large array of elements, you have 1, 2, 3, 4, 5, and so on, and your for loop passing through these elements one by one. Please close your laptops. Please close your laptops. Imagine you have a for loop passing through the elements one by one. Now, the last one will be executed really last, okay? Although sometimes they are independent of each other. So this is, for example, adding 2 elements here, adding another 2 elements there, 2 elements there. So they are really independent of each other. So unrolling meaning you really don't have to go in sequential order, okay? You can execute any of them in parallel. You can distribute this to a thread. This is another thread, another thread, another thread, another thread. And you can execute the entire for loop just in 1 second, for example. Because they are independent element, and you can do that. Some of the compiler allow you to add pragmas. Pragmas mean extra instruction that you can write next to the for loop. You can consider it as a command. So, but normally has special sign like this. So it's not like the double slash. Okay, so the compiler understands that this is a pragma and not a command. Okay. And you can use those special pragmas. They are very dedicated. So you have to know the list of pragmas allowed for you to use. And you can write like enroll loop, for example, next to the for loop. That the compiler is going to do all that job for you. You don't have really to distribute those elements into threads. All right. Hopefully everything so far is clear. If you have any question, please ask. Now we'll jump into the first form of doing the actual processing in memory. Okay. Hopefully by now you remember how the DRAM device works. How many of you still understand the 3 commands we use for DRAM? Activate, read or write, and then pre-charge. How many of you still aware about the 3 commands? 1, 2, 3, 4, 5. Yeah, I want to see more hands. Okay. Almost the entire class, except 2 ladies. Okay, now I have one slide for you, if you still don't remember. So the first paper called row clone. Cloning mean making a copy of something, right? So row clone meaning I'm copying a row. And again, remember this is a processing in memory. Okay, so everything has to be done inside the memory. I shouldn't go to the CPU and copy the element. So here's an example. I have the main memory, a memory controller, a hierarchy of caches. I want to move a data through the CPU to copy it and send it back to the memory. So I activate one row, go back to the caches, and then to the CPU, and then send it back to the row where I want to copy this entire row. Now, what are the problems here? I have three main problems. First of all, I have high latency because you know all the issue with the DRAM device. I have to pre-charge it. I have to refresh the entire DRAM. I cannot access more than 8 bits from each chip, and I cannot access the entire row. I can fetch it, yes, but I cannot get it to the data bus. I have to send column by column, right? So all of those we consider as high latency. But also I have problem with the interconnect since this is in a chip and this is a separated chip. So I always have interconnects that suffer from high bandwidth and also energy. And another problem is the cache pollution itself, meaning that I'm transferring data that will not be used at the CPU at all. So I'm filling the cache with data just to copy them and send them back to the memory. That's it. I'm not doing anything with it. So I'm filling the cache with actual data, but that's why I call it as a cache pollution. So I'm polluting it with data that I don't need. All right, and that the total time it needs to do this entire process, and that is the total energy spent to do that copy, just copying one row in the memory. Now let's see how we can do it. We want to do some process inside the DRAM itself, so that we just do this. 1, 2, just like that. Now we're already doing that by activating one row and opening the sense amplifier. We're already copying everything in the capacitors stored to the row buffer, right? So it's kind of copying that row to the sense amplifier, right? However, the sense amplifier is not part of the memory. It's not part of the matrix itself. So I have to maintain it. I have to move it somewhere else. So what I can do, now of course, we solve the three problems we discussed if we can do that inside the memory. And how we can do it is basically as the following. So we activate one row as usual, right? Now, once we activate it, we can read it into the row buffer. So we move it into row buffer. Now, what we can do, we cannot pre-charge. If we pre-charge, we are going to lose everything stored in the row buffer. What we need to do, always when you have, for example, a cup of juice or 2 cups of juice, and you want to move it into an empty one, you need to have a temporary location or temporary cup where you have something over there, and then you can move it to the 3rd cup, for example. Likewise in here. Before I move it from the row buffer, I have to activate another row. So I choose like randomly, or you could have based on specific address coming from the memory controller. You activate another row. Remember, the row we activated was a bit above that row. So that was a different row. And we didn't pre-charge it. So we just opened 2 rows. And now since this row is active, everything in the row buffer is going to share the charge with the capacitor above. So if the charge over there is above the threshold, which is half VDD, and that one was empty initially, then the charge over there is going to be shared between the two. So I'm going to charge that row with the exact same values I have in the row buffer. And this is basically how I make a copy out of the row. And this is how I save energy and the time by doing so. Remember this, the latency, the total latency, including everything was involved in the data movement, which is all caches, all DRAM, and all the interconnects. All right, so I can copy within the same matrix itself by just activating 2 rows and use the row buffer as intermediate storage, and then I move back to the new row where I want to copy, or as a destination. Can I do that between subarrays? Remember, the chip itself has several banks, right? And each bank has several subarrays. Now, everything we discussed earlier was within one subarray, one matrix. It's easy since I have the row buffer connected to all rows. So it's up to me to which one will be activated and which one will be sharing the charge with the row buffer. Now, with the subarrays, I don't have any connects, any interconnects between the subarrays. The only thing I have that all of them can see the data bus. All the subarray can send something to the data bus. That's why how I activate one of the subarray. Now that subarray will send data to the I/O interface of the chip through the data bus, for example, right? But how to send from one subarray to another subarray, that's not enabled by DRAM. So I still need to add something else to the subarray, for example, to share the sense amplifiers between the subarray, so that I move to sense amplifier and now do something with that sense amplifier to not share the charge with the bit lines or the rows, and move it to another subarray where I have the sense amplifier, and then I can move from one sense amplifier to another row in different subarrays. Now, this is extremely expensive since I really need to change the structure over there, and I need to expend more cycles to move data from one subarray to another subarray. Remember, only one subarray and only one bank can operate at a single clock cycle. What is a bit easier than that is to move between banks. Instead of moving within one bank between multiple subarray, I want to move from this bank to that bank. Why is this easier? Because the entire bank is connected to the data bus, and this is connected to the data bus, and I really don't need to worry about the subarray itself. The only problem with me, or with the design, or the actual DRAM, is that this data bus already connected to the interface or to the memory controller. So if I put any data over there, it's not going to be directly shared with the other bank, but it's going to be placed on the data bus itself. So I have to do something over there to disconnect or to remove that connection, and then it will be shared automatically with the bank, and then I can place it in the activated bank or activated subarray inside that bank. So this is one DRAM chip. I have two banks. I consider one of them as source, the other one as destination. I can activate that source row. Things will be moved to row buffer. And then I need to do something with the I/O bank in order to not exit the chip as output, but I want to place it still inside. And that's what they call it as transfer operation. And this is something new. They invented, they introduced that operation to the DRAM device. So once I transfer the data from there to the destination bank and avoid transferring it as output outside the chip, then the things will be placed directly in the row buffer because they are directly connected with the I/O of the chip. And then I can move everything with the row buffer to a destination row by just activating that row, and that row starts sharing the charge that's already inside the row buffer. Is it clear how we place one row from one bank to another bank? Now remember, there are something new that they introduced to the DRAM device itself. So it's not as traditional DRAM device. If we are interested in looking into the operation itself, this is traditionally how you would copy a row, okay? Hopefully now it's clear how we do the operation with the DRAM. Is it clear? Should I repeat the operation? You understand the three operations now. Activate, read, and then pre-charge based on sharing with the sense amplifier. Okay, perfect. Now the first one is the traditional one, where you move the entire row to the CPU, copy it, and send it back to the DRAM. How you do it? You activate one row, and remember, you cannot read the entire row to the CPU. What you would need to do, read column by column. So you got the entire row, yes, but there is a column decoder. Based on the column address, you can fetch them one by one. So you would need to send this command, read one, read two, read three, until you read the entire row, and then you pre-charge that row, meaning that you close it, done with it. I already moved to sense amplifier. Now I want to activate another row in the memory. And then write one, write two, write three, until you write the last column of that row, and then you pre-charge whatever you activate there as a destination row. This is how you would do it normally, okay? Now, there are two examples here. The moving between subarrays is not shown. moving between two subarrays not shown because it's really complex, and the operation or the commands that I send from the memory controller are not usual. Okay, they introduce their own commands. Now the first one is the easiest, where you just transfer within a subarray. So what you need to do, activate two rows and then pre-charge both of them. Pre-charge both of them. Why? Because both of them hold the same copy. So it doesn't matter which one you pre-charge earlier. So you just activate source, then that will be directly shared with the source amplifier. Now you activate the second, that will be connected to the sense amplifier, and then you pre-charge both of them, you close them, then the data already maintained over there. How you move it between banks? Remember, we introduced a new command called transfer. So this is not read, not write. This is related to read and write together because you read from one bank, you write directly to the other bank. But remember, transfer, it's about disconnecting the IOs, the output of the chip. I don't want to transfer the data through the data bus. Otherwise, I'm losing the benefit of processing in memory. So I activate source, I activate destination, so it will be able to receive any data I send through the IOs. And then I transfer one, transfer two, transfer three, because the interface of single bank is only one column. The size of it is really one column. I cannot transfer the whole row. So I have, again, to transfer column by column as long as I'm outside the bank. But over here, I'm inside the bank, and I'm inside the subarray itself. So I don't really have to go through the column decoder. I don't really need to transfer the data column by column. That's why over here, I have to wait for about 64 cycles to transfer the entire row between the banks. And then you can pre-charge or pre-charge these two different destinations, or source and destination. All right, this is about the additions that they have to do to the DRAM device itself. Okay, so we already discussed that they have to introduce their own hardware to the DRAM, meaning that whenever you play with the DRAM device or the actual hardware, a manufacturer should fabricate this DRAM device, meaning that this is only research and you cannot do it in your own. Okay, you cannot just change existing DRAM into row clone enabled DRAM, right? So, but still, all the changes are minimal, except especially when we talk about subarray or within a subarray or bank to bank. But between subarray and between another subarray, that's really expensive. The overhead to in terms of area and the hardware you need to transfer between two sense amplifiers in different subarrays is really expensive. And we will see that it doesn't have really benefit in terms of latency. So the first addition they have to do is to the DRAM chip itself, because they need to introduce that transfer command, for example, and also the DRAM interface itself. Okay, why the DRAM interface? Remember, they have to do something with the I/O of the chip. They have to disconnect it from the data bus, and then the two banks will be connected together, and then they can transfer the data between the sense amplifier. How they can do that? The easiest thing is to use MUX, multiplexer. Multiplexer meaning that I wanted to direct one input to that output or to different thing. So a multiplexer normally, this is the icon of the multiplexer. I have several input, and I have some controller over there. So you choose only one of those inputs based on the binary bits over here. If you write 0, 0, that will be chosen the first one, 0, 1, the second, 1, 0, 1, 1. Based on those controller, you can choose which input to be directed to that out. So you can use that MUX to control the direction of the data movement between the banks, for example. And the area overhead that you need to pay extra in terms of silicon where you fabricate this MUX is really negligible. You can consider it as 0.01% of the area. And in terms of memory controller, what they need to do is to introduce this command that is 2-cycle command. In the first cycle, the controller send transfer with the source bank ID and the source column index. And remember, We cannot transfer between banks a whole row. That's why we need the column ID. One by one we send, okay? And then whenever we send, we need a place to receive. So we need directly to send in the next clock cycle where to receive that column. So every time we want to copy a column, we have to send two commands of transfer. One of them with the column ID, where we need to get that column, and the other one where to send that column. Okay, that's between the banks. But we don't have to use the transfer command if we want to copy the rows within the subarray itself. Now here are the some results. You can see this is where you transfer the row into the CPU. So traditionally, how you would copy a row, you send it to a CPU, and this is normalized to that execution time. So now the fastest design is intra-subarray, which is within a single subarray. You just activate two rows through the sense amplifier, you copy that row, and that's it, done. That is the fastest design that you could achieve. And also the most energy saving design, because you don't utilize the interconnect that is outside the chip. You don't move from one bank in one chip to another bank in another chip, for example. The green one, as is expected, is the interbank, where you transfer data or rows between two banks. Okay, it's a bit more expensive, a bit more time consuming, because you don't do it within the same DRAM matrix. You have to transfer to another matrix through the interconnects, and you have to disconnect the data bus from the connection and then send two transfer per two cycles. So instead of sending one read per single cycle, you are sending two cycles or two commands per two cycles. Now the third one, which is the most expensive one, is the inter-subarray, meaning that you are copying a row between two subarrays. And that is the most design, the most expensive design in terms of both latency and energy. Is it clear? You understand how we enable computation? Of course, this is simple computation, just copying a row. We are not doing like bitwise operation and so on. However, it's really important in terms of the application. Let's see some application where we can use that. Probably you are aware of some of those applications where you all the time copy data from one place to another. For example, forking. You fork could be a thread, could be a process in the operating system, and so on. But it also could be zero initialization. What does it mean? So last time Mansour asked about, what if the entire subarray of the DRAM was zero? Do I need to pre-charge? Because I'm not going to lose the charge. It's already zero, right? So here's an answer. If you want to initialize the entire DRAM chip with zeros, what you would do? You initialize one row in the DRAM with zeros, the entire thing with zeros, and you copy it multiple times. You keep copying to all rows, so you activate the source and any destination, wait a few cycles until the row buffer read it, and then it will be copied. Repeat that many times to all destinations, and then you are initializing the entire chip or the subarray with zeros. But can be also used in many things. One important point is that these two operations, which is basically copying a row in the array, how many of you are aware about mem move or mem copy? How many of you do C programming? How many of you do GPU programming? You should use any of these two, either in CUDA, there's CUDA mem move, right? Or in C, you could use the mem copy, right? So any of those two operations accounts for about 5% of the cycles in Google Data Center. So most of the work you are doing, either by copying a video or uploading a video or doing your Gmail, some copies of the Gmail in your mobile device, in your laptop, and so on. So all of those try to use a mem copy or copying rows inside. That's the paper. It was introduced in 2013. So if you're interested, you can read it. Great. We have more time to go through more papers. I think I have 16 papers to cover for processing in memory. We'll see how many of them we can cover, and we can leave the rest for next week. Okay? Why are you sleeping today? All of you. Don't look into each other. You have exams? You have something? Who's getting married? No one? Not yet? Who's getting married tomorrow? Oh, really? Who completed his qualifying exams? Should we celebrate it? I was his examiner. Yeah, we should celebrate most of the time. So you should find an excuse to celebrate anything, basically. All right, the next example, we're trying to do more sophisticated computation. So instead of just copying, okay, it's used in 5% of the data center, but we need more sophisticated computation. Let's look into something called ambit. Okay? Again, this is where we are going to use the DRAM device itself. We are not going to add engines to the DRAM, but actually using the analog operation happening inside the DRAM device. We're going to enable a number of operation. The first two are not enabled by ambit, but rather enabled by row clone. So this work, try to use the previous paper, okay, to do the first two operation, which is copy and zero initialization. Zero initialization is basically copy, right? You just initialize one row with all zeros, and you copy it multiple times. Now, what is new here is that they are introducing and, or, not, and the majority operation. The majority operation is basically and or together. We will see now an example of that. So what is new here is and or. The not operation is also naturally provided in the DRAM. We will see now how. This is at low cost, using analog computation capability of DRAM, meaning that they leverage the command activate, pre-charge, and read, all those commands to do their own operations. The idea is to activate multiple rows to perform computation. We will see how many. So there is about 30 to 60x performance and energy improvement by doing so. This is the paper introduced not in 2017, although this paper, which is with title Ambit, introduced in 2017, but the same authors write an earlier copy in 2015. Okay, in the title there was no Ambit, so they was doing an expensive job to achieve this operation, and then they rewrite the paper with more nicer way of doing the same operation with a cheaper cost. Okay. This is a reminder, if you're not aware about the DRAM cell, how we do it. So remember, there's a word line. That's why we call it word, because connecting all bits in one row. That's why we call it word, meaning that more than bit, it's connected with the same line. But here, it's a bit line, meaning that only single bit is connected to that line at the time. Okay? You can connect it to any bits within the column, but only one of them should be connected to that bit line. And there's an access transistor that enabled to charge or discharge, so you can open or close it. Sense amplifier will get that charge. So first you enable the word line, you enable the bit line, you get the charge from there through the bit line. The bit line by default is half VDD, and then it will be shared among both of them. Now, if this is full, this is half, they are going to share somewhere in between. Okay, and that somewhere in between, we call it as delta. We're going to add it over there. And now the sense amplifier will sense that this is above a threshold, and then they are going to amplify it into full VDD. And then that full VDD amplified by sense amplifier going to be shared with that capacitor. Then this will be fully charged again. And this is how we maintain the operation. This is very important. That's why I repeat it over here, because now we will see what will happen. Remember, we are going to achieve and, or operation. So and or operation. The idea behind this is to activate 3 rows at the same time. So you send activate, activate, activate. Okay. Of course, you send the address of these rows, so you already know which of these rows being activated. Now, in this example, assume this is already fully charged, this is fully charged, and this is empty, okay? Now, you are going to connect all these transistors because you activate them, so all of them will be connected to the bit line. Now, the bit line is confusing. It's no longer bit line. You can call it word line, for example, or bits line, because we are not connected only single bit. Now, what will happen? Remember, always the bit line is initialized by half VDD, which is our threshold. Anything above the half, meaning 1, anything below it means 0. Now, I have those charges. Whenever I connect, they all will be connected with that bit line. And remember, when I connect a wire to many capacitors, means I'm sharing all charges together. So it will be equally distributed among all capacitors. Now I have, in the first one, full VDD. I'm not sure if you can see the lower side of the board, or maybe I can erase somewhere. Maybe I can use another color. I have red, I think. Okay. Yeah, the first one, what I have is VDD, right? The second one, I have another VDD. That is 2 VDD. This 2 VDD distributed over 3 capacitors, because now I'm going to connect all of them with one wire. That is, will be 2 over 3 VDD per capacitor. Let's see that. I connect all the transistor. Now the charge is shared among all capacitors, right? But it's not half. It's 2/3 VDD, okay? A little bit more than the half, meaning that I'm initializing all of them with ones. Remember, previously there were 2 of them only ones, and the third was 0. What does that mean for the sense amplifier? Now, the sense amplifier, I always was showing it as a black box, okay? Just sense amplifier, but we never know what's inside it. I told you once in the back that the sense amplifier is differential circuit, meaning that this sense amplifier provide me the positive and the negation of that positive. So whatever I'm sensing over here, if it is 1, I also have 0, which is the negation of the 1, right? Which is not circuit. So if I'm sensing 1, I also have a copy of 0, which is the NOT or the inverter of the input. This is how differential circuit works. So we have 2 NOTs, and depends where you read. If you read from here, it will be the original value. If you read from there, that will be the negation, the NOT value, okay? If you read from there, you are reading the positive value. So this is how you perform NOT, but this is not related to what we are showing over here, just to give you an insight why we have 2 inverters over there. This is not added by ambit paper, okay? Now, since it's 2/3 of the charge, so there is a delta added to the half VDD in the bit line. Now the sense amplifier will sense it as a 1, and we will have a 0 over there since this is a NOT gate. Now what happened basically, so now, yeah, of course, the amplifier is going to amplify the signal, and then all of them will be 1s from 2/3 VDD. All of them will be 1. But what happened, if you realize or if you follow the operation of what's happening, there was 2 of them 1 as input, and 1 of the input is 0. Now the output becoming 1. What does it mean? This is what we call majority circuit. Majority circuit meaning that if more than half of the input having a value of 1, the output is always 1. And previously, I have this as 1, and this as 1, and this as 0, meaning that the 1s are majority than the 0, then the output is 1. And when you look into majority function, this is the equation for the majority function. A times B plus B times C plus A times C, okay? That is a bitwise function. This is a very famous function called majority function. And in order to have a 1, at least 2 values should be 1 for the final state to be 1. If it has more than 3 operands, then we said more than half of the input should have value of 1. Now, okay, where's the AND gate? Where's the OR gate? You just convert that equation into this. You just take the C as common between B and C, and then you take the C bar from A and B. Okay. How many of you still remember how we do optimization from this equation to that equation? Yeah. Probably you need to remember digital design. Just to need to check how we got this from that. Okay. All right. Now, how we can realize and from this equation? It's already there, right? What do I need to do to activate this? A times B. I need to make C bar as a 1, right? If C bar as a 1, meaning that the input is 0 for C, right? If input is 0, meaning that I'm canceling this, so it's no longer OR operation, and I'm activating this, now it will be A times B. So if C0, A times B, it was initially 1 and 1, 1 and 1 mean 1, okay? You can try yourself for 1 and 0 and see how, for example, if these two zeros, and this is 1, meaning that I'm doing AND operation. Now 1 and 0 should give me 0. Now you can share all the charges, one of them VDD. Now I'm sharing one VDD over 3 capacitors. What is the value of each capacitor will be? 1 VDD shared among 3 capacitors. 1 over 3, right? 1 over 3 VDD. This is less than a half or more. Less means it will be 0. So in fact, it's doing AND operation, right? Now if I want to do OR operation, what should I do? C as 1, right? I'm canceling the AND operation, I'm activating the OR operation, and by doing so, I'm doing AND bitwise or OR bitwise operation for the entire DRAM row, okay? Is it clear? All right, perfect. Yeah, so hopefully we'll end up soon. I have, I think, 3 slides to finish MBit. We still have 4 minutes. Okay, so what they need to do is basically perform bitwise AND operation of 2 rows and A and B, and store the result in a row C. Okay, so what they need to do? So for activating AND operation, we said we have to use zeros, right, for the third operand in order to activate the AND operation and disable the OR operation. So that's why we have to fill a row with all zeros. So whenever we activate that row, every time we read a bit from that row, it will be 0, so that the other 2 rows going to perform the AND operation, right? So that's why I need an entire row filled with zeros. So every time I activate this row along with other 2 rows, one of them will be 0, the rest will be A and B, and this is how I will perform AND operation along the entire row. Okay? If you are confused, just go back to the previous slide where C should be 0 in order to do AND operation. Now, if you want to do AND operation for the entire row, C should be all filled with zeros, right? And how to initialize a row with zeros? You should have it in advance, stored somewhere, and you do row clone to that row into C. So now C becomes all zeros. Now, if you want to activate OR, you should also have another row filled with all ones stored somewhere. Whenever you want to do OR operation, you just do row clone to the ones into C, and this way you enable the OR operation. So that's why we need all the time 2 rows out of every sub-array just reserved for MBit. And that you can consider as overhead. We are wasting 2 rows. We cannot store data on them. We cannot use them. Memory controller cannot request them. So we need to block the addressees from sending any request to those 2 particular rows. Those reserved just for MBit, okay? And that can be considered as overhead for MBit. And the other 3 rows also should be reserved for MBit because no other request should interfere with these 3 rows. Remember, these are just intermediate as a controller. Every time we want to use them, we have to copy one of them into C, which can be any of those 3 rows. Okay, so you can consider this as A, B, C. C as a controller, either as zeros, you move R0 into D3, R1 is ones, you can move it to D3. And those is where you store the actual data, D1 and D2, okay? So you row clone A into D1, row clone B into D2, and then row clone R0 into D3, and then activate D1, D2, D3. Now they share all the charges between the 3 rows. Now you do the operation, and then you move the result to anywhere you want. The result will be already in the sense amplifier. So it depends on where you activate the next row. Directly, the result will be stored in that row. There is some changes that you need to do, similar to the row clone. So there is those number of rows that should be account for the input, a small row decoder to control these 3 reserved rows, a variation of activate command for activating 3 rows at the same time. So either you have a dedicated command in the memory controller to activate 3 at the time, or you send 3. Can you send it one after another? Maybe not, probably. Because if you send activate, then another activate for another row, and then another activate for a 3rd row, probably the charge might not be probably shared correctly among all of them. So either you activate all of them at the same time, or it depends on the architecture. You could send 3 consecutive activate to those 3 rows. The DRAM and the controller should support row clone, because we already know that the DRAM by default does not support row clone. So we have to add that mux, and we have to introduce the transfer command in the memory controller. So the row clone itself incur very low cost. We saw that already, which is 0.01, which is only the mux. It requires reserving 5 rows. Why 5 instead of 3? Why 5 rows instead of 3 rows? We need an ambit. There are the three rows that we deal with, A, B, and C. And there is the zeros and ones that we need to copy to the C, depending on the operation that we are going to do. The total operation, or the total number of rows that we reserve in the subarray compared to all number of rows in the subarray, is about 0.5% of those rows, which will just be reserved to ambit. Assuming we have about 1,024 rows in one subarray, in one matrix. So only reserving 5 of them is not really a problem. It's just less than 1% of the overhead. That was the paper. This is the older version I mentioned, 2015. And how we know whether this is the old one or the recent one, you just look in the title. If there is no ambit there, means this is the older one. The newer one in 2017 introduced and has ambit in the title. The NUT, we already discussed it. Maybe we can start next lecture, because there's just a little bit trick about it. I need to tell you about it. But remember that the sense amplifier over there is differential circuit, so we already have a NUT gate over there. Yeah, I don't want to take more time. I know we still have 10 minutes in the lecture, but no? Yeah, last 15 minutes, normally optional. It's up to the lecturer. He wants to grant you as a right, or maybe not a right, privilege maybe. All right, yeah, let's end up here and continue next week with more examples of processing in memory. And whoever getting married, congratulations again. Chocolate? Yeah, I know. Yeah, remember